Morning, everyone, and welcome to our webinar. Today, I will do the house rules and then I will hand over to our facilitator. I'm going to share my screen to do the house rules. Welcome to our Darasi webinar, Municipal Roadshow Water Quality and Health Series, Part 1, Balancing Microbial and Chemical Risk in Drinking Water Disinfection. This is our housekeeping items. We request that delegates only make use of the video function when speaking. Remember to look at the camera, not the screen. Mute your mic if you are not speaking. Use the chat to post questions or raise your hand to share ideas and engage in our webinar. Wait for the facilitator to call on you or unmute your mic. Presentations will be made available after the event. This is how you access the Q&A. At the bottom of your screen, there's a block participants next to it, Q&A. Please, can you post all your questions there? Our panelists will either respond live if we have enough time. If not, then they will just type in those questions to keep the conversation going. And then the webinar chat, it's next to the green button. It says chat. I will request that we carry on using that one, introducing each other, and then also carry on with the conversation. This is our program. I will just pause for like a few minutes and then so that people can just look at it, and then I will hand over to Nantantla, our facilitator. Over to you, Nantantla. Thank you.
All right, thank you very much, Tobile, for covering the initial housekeeping rules. Welcome, everyone. My name is Nonhlanhla Kalebaela. I work at the Water Research Commission, and there I am a research manager, and I manage a research portfolio that is largely on municipal water quality. So welcome to today's event and welcome to our speakers, and thank you once again for accepting the invitation to be part of the webinar today. So Tobile has already given a snapshot of our program today, and I'm hoping that we can interact a little bit more because as you can see that we don't have a long list of speakers really, and maybe what I'm going to suggest that instead of maybe keeping the discussion towards the end of the presentations, please feel free as a speaker is making the presentation to jot down your questions using the Q&A, as Tobile has said, or alternatively, you can also send an email if you would like to have an extended discussion on any particular matter that you might have picked up from the presentation. So without further waste of time, we are going to kickstart our program for today. The only information that I would like to share with you from the program is that we have one speaker who will not be able to participate live, but we do have a recording for Dr. Savia Murray from Rainwater. So if you do have any specific questions, please do send us a note and then we'll pick up your question and then we will make contact with Dr. Amarai. And then after that, we can then interact, or we can also, if there's anyone also in the audience who can also answer that question, please feel free to do so. All right, if you look at our program, the very first person in our program is Dr. Mandla Msibi, who's supposed to do the welcome from the Water Research Commission. Dr. Msibi, are you ready? I can see you are connecting right now. Are you ready, Dr. Msibi? Dr. Msibi, are you there? All right, while we're waiting for Dr. Msibi to connect properly so that we can hear him, I'll just like to do a recap once again of our program for today. So we have two sessions. So the first session is really an overview And under this session, we have a welcome by Dr. Mandla Msebi, and then we are going to have Ms. Liane Kutsie, who's going to be talking about drinking water quality standards for South Africa. And then after that, we're going to have Mr. Samuel Diarra, who's a senior advisor, wash quality and innovation from the Global Center for World Vision. And then after that, we're going to have Ms. Pesantha Madure from Umgeni Water. And then after that, we are going to have a recording by Dr. Safia Marais from Rainwater. And then after that, there was an allocation for a discussion, but as I mentioned, we do not necessarily have to keep your questions towards for that session only. Please feel free to actually send us your questions by using the Q&A box. And then session 2, where there is a presentation of case studies from different municipalities around the country. So I would like then to check if Msebi is now available to welcome us. It seems you are connected now.
I'm trying to make sure my, can you hear me?
We can hear you, but we cannot see you.
I've just managed right now to finish downloading Zoom. So there was a problem connecting. Okay, I hope
Fantastic,
now
we can see you now.
Thank you so much. Thank you so much. Let me take off this tag. Colleagues, let me just take this time to welcome you all to this wonderful webinar. I've gone through the agenda, and I happen also to be very much aware of the type of work that the Water Research Commission has been doing or supporting during the past years concerning treating drinking water in small waterworks. We also learned over the past years that actually, for some reason or another, small waterworks tend to provide a unique challenge as compared to large waterworks. So there has been that particular focus on trying to really understand and make sure we can really characterize the small waterworks and understand what is happening to ensure that our water treatment processes are free of any risk to our water consumers. So we acknowledge that we need that special focus on small waterworks. We acknowledge that we need extra work, we need extra effort to try. Disinfection is one of the most critical steps in the water treatment. I always say when I travel with my family to a small area, and for you to drink the water, one of the things, it will look clear, which is fine. But if I can smell a disinfectant like chlorine, I feel much more comfortable, and I know my chances of being safe here are very, very high. And on my side, I can drink the water very comfortably or with confidence. So is the important step of disinfection. This report number 2809, it's a very critical report, and it will actually address some of these challenges that I'm actually outlining, that I've just outlined. The report is titled Investigation into the Influence of Hydraulic Conducting on Disinfection Efficiency in Small Waterworks. And it deals with the microbiological risk in terms of the water quality and also the chemical risk in terms of the water quality. With that said, I also want to congratulate the team that has worked so hard to put this work together, to carry out the analysis and the studies, and also congratulate Nonhlanhla, the research manager, for putting together this and leading this wonderful piece of work. I truly, truly expect that this is going to be a wonderful, beneficial, exciting engagement today. And I want to encourage all of you to read this report from page 1 to the last page for the benefit of all our communities in South Africa who cannot live without good quality water. With that said, I thank you and I welcome you all to this wonderful webinar. Thank you so much.
Thank you very much, Dr. Msebi, for those welcome remarks. And indeed, disinfection is a very important subject or topic area in drinking water treatment. And as we know that, in the past, disinfection was very important to make sure that you disinfect adequately so that you can eliminate microbial risks. But what we've seen in the recent years is that we have also seen that over disinfecting might also present risks, such as the formation of disinfection byproducts. So today, really, that is the gist of the event today. And fortunately, we have a good mix from our international partners who are going to share with us from insights from their areas. And also we have also a mix of case studies from your smaller municipalities, as well as your bigger water boards. So I expect that today would really be a very good learning session, and also an opportunity to also interact in the case that you have any operational challenge that is related to disinfection. So we can really have that discussion, and then if there's anything that you're struggling with, I think this is the ideal platform to actually maybe have that discussion and see how other people really are dealing with challenges in their municipalities. All right, so we are going to move away from that very first item, which was the welcome remarks. And also I want to reiterate by also welcoming everyone and our speakers for today. And then I am going to move on to the very next speaker for today, Mrs. Leanne Kutsia. Leanne?
Hi there, Nontlandla.
Hi, Leanne. Over to you.
Thank you so much. Morning, everybody. Thank you for this opportunity. I am going to quickly share with you the drinking water standards. There we go. So I'm going to be telling you a little bit about the work that the committee is doing and the drinking water standards for South Africa. It's falling right into what we're talking about here this morning, because we're talking about risk, and we're talking about disinfection byproducts and chemical risks. So for the drinking water standard that we're busy making or busy producing today, and what I'll give you a little taste of today, it's going to be an interesting and a new development for us for the next round. So let's quickly talk about standards development. You can see here that it's not a quick road to develop a standard. We start with preliminary work items, which is like if somebody's got an idea for a standard, then you would draw up a preliminary work item, and that would become a proposal for the committee. Then if it's approved by the committee, it becomes a working draft. From a working draft, it goes to committee draft. From the committee draft, it goes to a direct South African standard, and then it goes to approval and then publication. So it's quite a road that any standard actually travels. And this road can be up to 2 years long. When we start looking at adoption of standards, a lot of the standards that we're using in the country are ISO standards or EN standards. Those can take around about 6 months. So it's a lot quicker to adopt a standard than to write one from scratch. The one that we're currently busy with now, and the one that I'll discuss with you today, is the SANS 241. And we're at a point now about working draft to committee draft level. So we've got a few weeks to go before we get to a publication document. Who sets these standards? Who's part of this committee? It's the members of the Technical Committee 147, which is a water quality group. And they are actually a mirror committee for the ISO TC, also Technical Committee 147. So there's a similar group that's based in Europe, and we do the similar work to what they do. And this committee is made up of experts from various water boards, municipalities, laboratories. It includes the regulator, the Department of Water and Sanitation, as well as research institutions and industry. So there's a variety of people who actually sit on this committee. And this committee does not only run the drinking water standard, but we do all the water quality standards for South Africa. The technical committee does 7 standards in total, where the microbiological committee, which is the steering committee for SC4, is 27 standards. and sampling is 7 standards, and then chemistry is 84 standards. So there's quite a few standards apart from the drinking water standard that we actually operate with and run with. So we're focusing today on the SANS 241. I'm hoping that everybody knows what the current standard looks like. And that standard is now in revision. So it's revised every 5 years. And we are aiming for 2021, which is now in working draft. So it's going to go to the committee hopefully in December, January of 2021. And then after the committee approves that standard, it goes to a DSS stage, which is the draft South African standard. And this is where last time around the Water Research Commission helped us a lot with public comments. So we actually put a link on the SABS website and on various other platforms to help us to get public comments on that standard. So I would recommend that you keep your eyes open for the DSS stage where you can actually comment from the public. This standard is also based on the WHO guidelines for health. So when we draw up a standard, we actually use the WHO guidelines for drinking water to check that our health-based guidelines are in line with the WHO. And if this time around, what we've also included is that if you are not sure about a parameter that you perhaps have as a risk in your water system, that you would refer to the WHO guidelines. It's actually a much stronger focus on looking at the WHO guidelines if you're unsure of the parameters risk. So this document is now written in a certain way, and it comes back to Dr. Msibi's comment about risk. The whole standard is written for risk, a risk-based monitoring and risk-based assessments. So you'll see there on the left-hand side, it says water quality risk assessment. You always start with that. That includes like anything from catchment surveys to historical water quality data, anything that you've got on that system, any information that you've got about that system that could help you to get to point 2, which is where you start listing hazards and potential risks for that water treatment system. As we all know, the small water treatment systems are generally higher risk because things go wrong quicker at smaller treatment systems. So this is also where you would point out your potential hazards and your potential risks. Based on those risks and hazards, then you would draw up a system-specific water quality monitoring program, which will be specific for that particular wastewater treatment, drinking water treatment plant. And then you would follow up with that system-specific monitoring program with some compliance monitoring. So that means your mandatory process indicators, plus the risk-based ones that you've identified in step 1 and step 2. That would be your compliance monitoring, which we all know is what we generally do. And then it goes back to the verification of performance, which we know from our current standard, where you actually check your performance against a certain set of criteria to make sure that you're actually performing correctly. And then, of course, that goes back to the water quality risk assessment. So we would expect you to look at that water quality risk assessment at least on an annual basis, but it's a continuous monitoring program. So even if you have a monitoring program in place and something changes in your system, we would expect you to change your monitoring program so that you could ensure that you cover those risks that have been identified. And this process is a philosophy for many ISO documents, and I think even the WHO document. It's all based on risk. So it's about that plan, do, check, act that we know so well, with the continuous improvement. So that's when you're using all your data to have a look, you can actually start monitoring and managing your risks better. And then next time round, you have less unknowns in your system. So what's new in SANS 241 2021? It's actually going to be 2021 by the time it's published. And once again, it's a risk-based approach as per the ISO and WHO philosophy. So I think that is coming out stronger this time around. Unfortunately, because it's not in DSS yet, I can't share it with you. So I'm just going to give you a little taste of what's to come. There's definitely more tables in this standard, including one just for disinfection and disinfection byproducts. So that's where we've actually included a couple more disinfection byproducts. Like THMs is already in there, but HAAs and the NDMA are actually also included in that table. And this is specifically to ensure that we cover all our disinfection risks. It also includes chlorine dioxide and chloramines as disinfection, and we provide in lower limits again. You'll remember that we took the lower limits out for the 2015 standard, and based on feedback from the sector, we've decided to put a lower limit back in for the disinfection standards. So, and that's including for chlorine as well. So there will probably be a lower limit, assuming that the committee agrees. There'll be a lower limit for all the disinfection chemicals. And we're also we've taken note of the desalination plants that are out there. So we're going to include a few more microbiological parameters, especially for those desalination plants and the high risk plants out there. So we're focusing mainly more on risk than size of plant at this point, because as we know, size doesn't necessarily mean that it's a higher risk. Another interesting development, and another one coming from the sector as well, is that we're going to be including some protection of infrastructure determinants. So you can expect something about corrosion potential monitoring requirements like calcium and magnesium, calcium carbonate precipitation potentials, so that we can ensure that the infrastructure is actually kept in a good state. And we've got an organic chemicals table that we are including for the first time, with various parameters that we think are going to be the key ones for agricultural chemicals and things like that. So we're going to include a chemical table. Another thing that we've included this time around is a section on monitoring of tankers and static tanks. That would be like those JoJo tanks that are put out for filling by tankers. So there's a special section in there specifically for monitoring the tankers themselves, as well as the static tanks. We've also included for the chemistry people, and the handling of uncertainty of measurement. So this is where it links to the ISO 17025, which is the laboratory standard of analysis. And decimal point usage, as well as the analysis of metals, how to analyze metals properly. This is also clarified in the document. And this time round, to make things simpler, I hope we've just got it as one document. So we don't have SANS Part 1 and Part 2 anymore. It's just going to be a SANS 241 2021. It's about 42 pages at the moment, but as I said, it's still not, it's going to committee draft now, so we will see if it gets longer or shorter. So in conclusion, I would ask you that when you see the new document, please don't just look at the tables, read the whole document. It has been extensively revised. Some of the people who have worked very hard on this document are in this webinar today. So thank you for them. And please it's not just only about the tables, it's about the whole document, the whole holistic process. And when we are ready to give you the draft standard, please make yourselves available for public comment. We will try and put this out on social media and on various websites so that you will be able to know when the draft standard is out for comment. And we would appreciate any comments coming from the public. So with that, I thank you very much.
All right, thank you very much, Leanne, for that very insightful presentation on the developments with regards to SANS 241. I don't see any questions for you in the Q&A box, but I just want to check quickly. I see Ramaliba G, who has a hand up. I just wanted to make sure that it is a question for Leanne. Ramaliba G, do you have a question? Okay. I assume you can hear me, but I cannot hear you. Please feel free to type out the question. Okay, I see it's a no. Okay, can you then please just put down your hand because I see that is up. All right, I think then we can move on. Thank you very much, Leanne, but please do feel free to post your questions under the Q&A if you do really, if something jumps at you or pops up during the webinar today. And as Leanne said, when the document is distributed, please do send in the comments because that is a sector document. Thanks once again, Leanne. I'm going to move ahead with our program and welcome Mr. Samuel Diarra, who is going to do a presentation that is titled Assessment of Trace Metals in Rural Water Supply System. Mr. Diarra, are you there?
Yes, I'm here.
Please feel free to introduce yourself as well. Welcome.
Good morning, everyone. My name is Samuel Diarra. I'm the Director for Quality and Innovation. Today, I'm going to talk to you about, I have an issue here, sharing my screen. I'm going to talk to you about the assessment of trace metal in rural water supply. Are you getting my screen right?
Yes, definitely we can see your screen.
Excellent. So my role today will be to ring the bell on the issue of trace metal in rural water supply. In our experience as NGO, I work for World Vision. We provide water to communities since 2003 as a large program. Today, we are reaching about 50 countries with our business plan, but globally, we are reaching more than 82 countries. But the experience I'm going to share today is about what we did in West Africa region, as West Africa has been the larger geographic area where we work for more than 20 years. We realized that water quality issues are very critical in the provision of safe water. And because of that, we conducted some water quality analysis, including physical, chemical, bacteriological test, but also trace metal test. We decided to sample our new drilling borehole between 2004 and 2018 to ascertain that water we provide to communities are of good quality. It happened that 2 years ago, we started reviewing our water quality database for about 3,400 wells to ascertain that we are not having some occurrence of lead. We tested samples in Ghana, Mali, and Niger. The key finding came out like this. We realized that we have 3% of our wells, newly drilled well, having lead accidents. In Niger, we realized also that we have about 9% and Mali 13%, which was actually alarming. We know that water quality issues, bacteriological issues are very highly considered, but trace metal can be also an issue. Then when we realized that those boreholes have exceedances, we decided actually to not equip the wells. And we decided to conduct a post-drilling monitoring 1 year after. And we realized that most of the borehole have some kind of depletion in the content of lead. And this was after 12 months period. We did some additional investigation in the field, and that investigation point out that the contamination is caused by drilling operation, mainly gravel used as filters, but also additive like polymers during the drilling process. The gravel issue is about adsorption and desorption process.
Mr. Diarra, you are on mute.
I'm very sorry for that. I don't know how it happened.
Okay,
Should I
we
go
can
back
hear you.
again? Are you hearing me?
We can
Yes,
hear
we can.
you.
Yes.
Should I go back again?
Yes, please.
Yeah, slide
No.
4.
Slide 4, yeah. Okay. After 1 year, we realized that there is a depletion in the content of lead in the borehole we assess. And further investigation helped us actually in the field to test the possibility of any geological contamination or agricultural contamination. And we realized that none of them was involved. So we concluded that the contamination is caused by drilling operation, especially gravel use, and also the quality of polymer and any additive we are using to drill borehole. And that post-implementation actually helped us actually to ascertain how the lead content is evolving over time. With that said, we realize as well that there is also some component of lead coming out of the borehole after installing the pumping system. It can be hand pump, it can be a submersive pump. We tested all of them by sampling water, 1 hour waiting time before sampling. And also we sampled the different parts of the pumping system and distribution system to analyze them. And the result came out like this. We realized that most of the system already in use for many years, and even the newly installed one have excess of lead compared to the standard. This is the example of Ghana, where we have 6% exceeding. We have 48% under the NS and GV standard. In Mali, we have 15% exceedance and 7% exceedance in Niger. And this comparison help us actually to understand that geographic area clustering is not the main factor. The water system type also is not the main factor, and the hand pump type, no. Then we understand that the water system age, some of them were more than 20 years of use, others were 2 or 3 years. We understood that this occurrence is happening regardless of these 4 factors. Then the study we conducted with UNC helped us to understand some of the root causes. The first is about the drilling input, gravel, polymer, any other material used to construct the facility. Why is that? It is about the quality of gravel, especially gravel collected from the riverbed, are highly producing lead. Polymers, we have seen also on the market that some polymers are not really made for water well drilling, but for petrol well drilling. And some material we are using for drilling is also are also considered to be producing some amount of lead. The second cause can be the presence in the source water, like associated with human activities, or the occurrence from natural sources like geology and hydrogeology. The third factor was associated with corrosion. And the UNC study, World Vision and UNC study point out that when we do the first flush evidence, we realize that after a whole night waiting time, the quantity of lead is high, very high. Even if we wait for 1 hour before taking samples, we have some high quantity. But when the pumping is taking place, this quantity is depleted. This is the evidence of corrosion taking place on the materials. Then it called for supply chain and procurement issue. The high quality needed for the water supply systems are not always available on the market, which pose the problem of supply chain. If we look at here, the issue of corrosion, we see that the brass material we are using are having high content of lead, over 0.25% of lead, compared to the standard of 8% lead. So this was one of the evidence showing that brass materials are having some corrosion, and this corrosion is releasing lead into the water. Some solution we want actually to suggest to this group is to ensure that we improve our policies, our water quality policy, to include quality checking for new borehole, but also for existing borehole, to ensure that the trace metals are not occurring as a result of any corrosion, or as a result of any material or any product we use for drilling. We need also to improve our procurement policies to ensure that quality materials, certified materials, are used in water quality facility, water facility construction. There is another component of water facility construction policies to ensure that those working in that field ensure that they are using certified materials and certified additives. The last component is about water safety planning. We know that there are some environmental contamination that can happen. We don't have at this level all the information about the environmental contamination, as our geographic area didn't have any, but it is a possibility. The second group of solution is to improve the analytical capacity. We know that many countries, especially in Africa, we don't have certified water quality lab. We are recommending actually to have certified lab where we can analyze our samples and build the capacity of government and any stakeholder working in the area of providing safe water to communities and urban cities, to ensure that the material we are using are of good quality. And we recommend also post-implementation monitoring, which will actually ensure that the water quality is monitored in the facilities to avoid any surprise in terms of increase in the production of any trace metal, and then to develop treatment facilities and solution for those water supply systems. As I was mentioning, the supply chain and procurement can be the main source of mitigating or even preventing the occurrence of those trace metal. And certified bodies exist already for plumbing material. And we can also talk to them, bring them in our policies, and ensure that we have a high standard water quality facilities, and ensure that we have good procurement systems in place. This is what I wanted to share today. I'm happy to answer your questions. Thank you.
Mr. Samuel, Diara, thank you very much for that presentation and also for sharing some valuable lessons all the way from West Africa on how you manage water quality, and also for stressing the importance of following a water safety planning approach. And I think I like your second last slide, because also it's giving us some food for thought on how we can also strengthen our current standards and also water quality policies with regards to really managing risks associated with maybe some of the infrastructure and equipment that we use for water conveyance, or it could be water treatment infrastructure, and their contribution to water quality. So thank you very much for that. I don't see any questions at the moment, but I will be keeping an eye on the Q&A. And if there is any question that is directed to you, I am going to let you know. For now, I am going to allow you to maybe listen on with the rest of our attendants, and we can pick up again during the discussion session if there is a question that pops up during that time. Thank you very much. And then I am going to move on with our program, and then ask Ms. Prasanta Madure from Umgeni Water to please proceed with the next presentation. So Prasanta was the project leader for that project that Dr. Msebi spoke about, where they investigated the disinfection efficiency in contact tanks, different contact tanks in small treatment works. All right, Prasanta, over to you. And I'm sure you will give a lot more detail than I did. And please also introduce yourself properly. Thanks.
Okay, thank you, Nanslansla. Good morning to one and all. As Nanslansla mentioned, my name is Prasanta Madure. I'm a process engineer at Umgeni Water, and today I'm going to present my WRC project, which is entitled The Investigation into the Influence of Hydraulic Contacting on Disinfection Efficiency in Small Waterworks. So it's quite a mouthful, so we're just going to get right into it. So our objectives for this project were to, as the title suggests, determine the hydraulic disinfection efficiency of the different contact tank geometries. So our focus was specifically on the geometries of the contact tank. And based on our results, to provide recommendations on how we can improve this disinfection efficiency. So the literature review into this topic has shown that the previous research has mostly focused on the type of disinfectant that's utilized in small water treatment works. For example, comparing your chlorine to sodium hydroxide, and what this impact was on the water quality by looking at the microbial results. Other studies were also focused on the hydraulic disinfection, which were mostly on a laboratory scale or a pilot plant scale. So this research is focusing specifically on the contact tank unit process of disinfection, as well as a full-scale research implementing it on live sites. The research also showed that small water treatment works, which are less than 2 megaliters per day, struggle to achieve adequate disinfection. This is for a number of reasons, and the research mentioned the low technical skills of operators, often in the rural areas, the lack of maintenance, as well as poor process monitoring and control, amongst other reasons. And as we are all aware, microbiological failures in the final water is a huge risk to human health. When looking at contact time, the theoretical detention time is often used to assess, which is basically the calculation shows the volume of the contact tank divided by the flow rate. But as we are aware, hydraulic conditions are non-ideal. So here we're also looking at the CT value, where C is the disinfectant residual in milligrams per liter required, and T is your contact time in minutes. So the CT value shows us that in order to maintain an appropriate disinfectant residual, if you have a shorter contact time, you will now require an increase to the disinfectant dosage in order to maintain that residual. The baffling factor is a factor used to standardize hydraulic disinfection efficiency. And this factor actually uses the theoretical detention time. It's determined by using the T10 value, which is the time at which 10% of the given disinfectant is observed at the outlet of the system. So we were able to get this value from our testing on the sites. The table below from the US EPA shows the various baffling conditions and the related baffling factor, from unbaffled conditions to perfect or plug flow conditions. So we use this table in order to assess the waterworks that were tested. When we were doing the site selection for the testing, a number of sites were surveyed, and while a number of them fell below 2 megaliters per day, it was difficult to find sites that fit all of the criteria listed below, particularly sites with distinct contact tanks with different geometries or with existing baffles. Other issues we had will be discussed later on in the presentation. So we were able to test about 4 sites that had different geometries and were less than 2 megaliters per day, as shown in the table. Site 1 had a circular baffle tank with no a circular contact tank with no baffles, which had a top inlet and a bottom outlet. Site 2 had a rectangular tank with a single longitudinal baffle as well as an underflow weir. Site 3 was a rectangular tank with no baffles, and Site 4 also had circular contact tanks. However, these were in series, with tank 1 having a top inlet and bottom outlet, and tank 2 with the bottom inlet, bottom outlet configuration. The experimental procedure for this research was using the tracer test analysis method. When we first went to site, we took the flow rate measurements, tank dimensions, and site criteria, and then looked at the disinfectant dosing point, where we inputted the tracer in order for measurement at the outlet of the contact tank. Initial tracers used with the fluorescein dye and sodium chloride solution in order to measure conductivity at the outlet. So contact tank design 1, I'm sure, is a familiar sight to most of us, the JoJo tank, which is used at quite a few sites as a contact tank unit process. So this plant was 0.25 megaliters per day with a single circular tank of 10 cubic meter. The second tank there was just as an overflow, and this tank has no baffles. So there's a top inlet where the sodium hydroxide disinfectant was being dosed. Calculations showed that the expected residence time for this plant was 22 minutes. But based on our testing, we found the tracer showed at the outlet after only 2 minutes, indicating severe inefficiency in the system. The baffling factor was then determined based on our results as 0.23, which on the US EPA table shows us it falls between 0.1 unbaffled conditions, and 0.3 poor conditions of mixing. So the test results indicated severe short circuiting, but when we looked at the historical data at the plant, we found that there were no E. coli out of ranges. So when we looked at it a bit further, we found that the final water is pumped from the water treatment works to a reservoir approximately half a kilometer away. And that is where the samples are taken for compliance monitoring. We then repeated the test for both the plant and the reservoir. So we found that from the plant to the reservoir, there was in fact a further 10 to 15 minutes contact time and mixing in this pipeline, which then allowed the plant to achieve this compliance. The second contact tank design we found was at site, which was 2 megaliters per day, a rectangular tank with a single longitudinal baffle, as shown in the photo below. So the flow was in at the bottom right, flew around, and then at the outlet point, samples were taken for conductivity measurement. Here, the theoretical residence time was approximately 21 minutes. However, we found that the actual residence time in the tank was 11 minutes, showing the inefficiencies in this tank as well. So although there was a single baffle and we were expecting a higher baffling factor, the results show still poor conditions at the site. From here, the water is pumped to a reservoir which is approximately 2 kilometers away, and the tracer test was repeated to determine the spike at the inlet to the reservoir. So we found that here there's another contact time, approximately 113 minutes prior to the reservoir. For the site, we were unable to get historical data in order to assess the compliance. Design 3 was a 1 megaliter per day plant with a rectangular unbaffled tank. The inlet pipe can be seen on the bottom right, with the outlet diagonally opposite. The results showed that an expected residence time of 246 minutes, which is approximately 4 hours. However, when we did the tracer test, we found that the actual residence time was between 10 to 14 minutes. So in this site, there was severe short circuiting, and the baffling factor was then determined to be 0.1 unbaffled conditions. Historical results available at the plant showed that chlorine residuals were within range, and there were a few E. coli detections over the 2 years data provided, which were less than 2 CFU per 100 mol. This plant as well pumps to an offsite reservoir. Unfortunately, we had some issues due to access, but there's a 1.8 kilometer pipeline, which should provide approximately 15 minutes of extra contact time. Design 4 was a plant that was 1.35 megaliters per day, which again was using JoJo tanks as the contact tank unit process. Here, there were 2 tanks connected in series, and the disinfectant was dosed in line prior to contact tank 1. The theoretical residence time for this system was at 37 minutes. However, based on the tracer test, we found the actual residence time between 16 to 18 minutes, again showing the inefficiencies of the system despite having the second tank connected. The baffling factor was then calculated to be 0.19, showing unbaffled conditions. At this site, there was no historical data available, and as mentioned in these sites, there was monitoring equipment on the site, but there were no quality records available for us to determine the compliance. From this site, it was pumped to a distribution reservoir approximately 4 kilometers away, and again, we could not access this or conduct the testing to determine the contact time. So results for the different geometries that were tested showed that the difference between the actual residence time compared to the theoretical time showed high inefficiencies in all systems. Having a single baffle did not improve the mixing at site 2, as there was still severe short circuiting of the site. The baffling factors assessed for all showed between unbaffled to poor mixing conditions. While testing on live sites, we did experience a number of challenges, or possibly we can call them lessons learned. We initially used fluorescein dye for the tracer test and added just a few grams. Unfortunately, this resulted in the oxide reservoir turning bright green, and we received a few customer complaints. So that was not done for any future testing. Pre-planning must be done before any of the tracer tests and analysis, specifically if there are level controls of the pumps on site. A number of sites have level control based on the on-site or off-site reservoirs, and if they're switching off and on, this will result in inaccuracies in the test results. One of the major challenges we experienced were finding sites that had suitable sampling points. As I mentioned earlier, we did survey a large number of waterworks that were below 2 megaliters per day, but couldn't conduct our testing because we didn't have suitable access points, either for adding the tracer or for conducting the sampling at the outlet. And quite a number of the waterworks also dosed the disinfectant at the clarified buffer tank, normally prior to a pressure filtration system. Lack of metering was another challenge experienced, where plants either did not have inflow or outflow meters installed, or sites that did have flow meters were not operational. So some of the conclusions from our research project show that the circular and rectangular tanks with no baffles have high inefficiencies in terms of your hydraulic disinfection. However, the negative impact to the consumers was reduced by the presence of pipeline or storage reservoirs before distribution. But we'd like to emphasize that this does not negate the need for accurate design of your chlorine contact tanks. Because when you're looking at the CT concept, if you're improving the contact time, you can optimize your disinfectant dosage. So you don't want to overdose your disinfectant, which could cause possible byproducts, as well as you're wasting chemicals, and this is an unnecessary cost. When assessing the water treatment system for troubleshooting, you should look at the system holistically when considering the disinfection process. Plant designers should consider residence time when looking at the disinfection process and allow for variable flow considerations. And when designing, also consider the baffles, the number and orientation of the baffles in order to maximize this contact time at design flow. In designs include sampling points. We also recommend computational fluid dynamic modeling to validate hydraulics, which could assist in improving the designs of contact tanks. In terms of recommendations, we like to have further investigations on sites with adding in modifications such as extra baffles or mixers, split inlets, to see if we can then improve the contact time at these sites. So Umgeni Water, in collaboration with Colorado State University, did start some testing at site 1, which was the 10 cubic meter JoJo tank, where we added in a modification to the inlet, changing the straight inlet into a 4-way inlet. As you can see by the picture, it was inexpensive and a simple modification. And we were able to improve the baffling factor from 0.22 to 0.52, which got it from poor mixing to at least average mixing. And we'd like to continue with this work and see how much further we can then improve the hydraulic efficiencies on sites. So I'd like to once again thank my reference group and project team for all their assistance during the testing, as well as Colorado State University for their partnership, Umgeni Water, eThekwini and 11 municipalities, and Mkhali's Water. And thank you so much for your time today. Thank you.
All right, thank you, Prasanna, for that very interesting presentation. And I mean, this is information that I really, as information is project that we do periodically to also serve as a reminder to the sector that disinfection is very important in every sector. Has very, very much detail of to ensure that there is
Hi, Doc. Please, can you switch off your video? Your sound is very bad. Just let's try and switch off your video, then you can carry on talking.
Right, thanks. Can you hear me now? I see that my voice is getting somewhere. Am I audible?
Hi, Chancellor, we can hear you, but the sound is distorted.
I am not sure why, because there isn't any problem that I see with my connection. But anyway, we can talk more during the discussion time. Sandra, I see that is actually for you, like Q&A. Please pay attention to it. And in the meantime, let me just try to reconnect again. I am going to give you the opportunity to link to the video by Sandra from
Okay, I'll share the presentation. I hope you can hear the sound.
Presentation, just a broad overview of the
and probably try to restart.
parameters influencing disinfection byproduct formation, the precursors, prevention and removal of DBPs. More about natural organic matter, NOM being the major contributor to DBP formation, typical THM formation in a large distribution system. How do we decrease THM formation without compromising disinfection efficiency? And then the take home. We know that disinfection byproduct precursors within the treated water react with the disinfectant, and DBPs are formed in the final treated water. Because we mainly use chlorination in South Africa for disinfection, we focus on its DBP that form, which is mostly halogenated disinfection byproducts like trihallomethanes and haloacetic acids. The formation and concentration of DBPs in water, drinking water, are influenced by source water characteristics, NOM, disinfectant type, and the concentration of the disinfectant, residence time, temperature, and pH of the water. So we have our source water, the precursors within the source water, and then the water that is treated at a water treatment plant. During the disinfection step, the DBPs form. More than 700 DBPs have been identified up to date due to various disinfectants used, different treatment pathways, and also because the source water quality greatly differs. These disinfectant byproducts that form are usually grouped into chemical classes: halocetonitriles, trihallomethanes, haloacetic acids, NDMA, etc. Now, in order to prevent the formation of potential carcinogenic DBPs, we can either remove the DBP precursors before disinfection, in other words, prevention methods, or we can remove the DBPs after they formed, removal methods. What is natural organic matter? NOM is the compound that gives water that brown-yellow color due to it being mostly humic substances. NOM is not a single compound, but it's a complex mixture of organic compounds with different structure and characteristics, and its composition is different in various source waters. Not all organic compounds will react the same way with a disinfectant to form DBPs, since the character of NOM differs. In other words, its molecular weight and also its hydrophobicity varies. And also the concentration of NOM greatly affects the formation of DBPs. NOM occurs naturally in all water sources, mainly due to the decay of animal and plant material, but it can also be flushed into rivers or dams during heavy rainfall. The major contributor to disinfection byproduct formation is NOM. If we use a different disinfectant, we will still form DBPs, but it will be a different DBP and not necessarily THMs. Because people will often ask, but what if chlorine is causing DBPs? Why don't we use a different disinfectant then? And the most important reason why we use chlorine is, yes, it is cheaper compared to other disinfectants, but chlorine provides a disinfectant residual. So if you have a big distribution network, or if water stays in a tank for over a long period, then chlorine can provide that much needed chlorine residual for microbial or pathogen control. The precursor mostly responsible for the formation of THMs and hallucidic acids is NOM. Because we mainly use chlorination in South Africa, we focus more on DBPs that will form during chlorination, being THMs and a small amount of hallucidic acids. And then we also focus on natural organic matter, which is the main precursor to the formation of this halogenated DBPs. So what happens if we do not adequately remove NOM during water treatment? Dry halomethanes are formed in the final water. The water will have an increased chlorine demand. Odor, taste and color problems might be evident in the final water, and insufficient NOM removal can also increase bacterial regrowth within the distribution system. This graph is a typical presentation of what happens in the distribution system. We see a clear increase in the THM formation, but well below the SANS 241 value. Within this graph, we see a decrease in free chlorine throughout the distribution system, but this specific plant has an adequate CT value at the primary station for the incoming bacterial load. At secondary disinfection, one wants to maintain this free chlorine residual, and that is then achieved by adding ammonia at this specific point. Here we see that the THM formed after disinfection is mostly bromodichloroform and chloroform, and again we see the increase due to longer residence time within the distribution system. But how do we decrease THM formation without compromising disinfection efficiency? It's very important that disinfection efficiency should never be compromised just to meet the guideline levels for THMs or when trying to reduce the concentration of DBP compounds. Now, the easiest way and the most effective way to decrease THM formation is to effectively remove NOM during treatment or decrease the NOM concentration as much as possible. If we increase NOM removal during treatment, if we increase NOM removal, the chlorine demand of the water will decrease. So we dose less chlorine, and then ultimately the THM formation will also decrease. But it's important to remove the NOM fraction that is mostly responsible for the THM formation in your specific source water. First of all, we determine this problematic norm fraction, mostly responsible for the TH information. So we make use of norm characterization techniques to determine the overall organic loading in the source water, the current norm removal, and which norm fraction are currently being removed by your treatment process, and to determine the trihalomethane formation potential of the specific or in the individual norm fractions. If we do not have advanced norm characterization techniques, we can make use of surrogate norm parameters like dissolved organic carbon, UV254, and SUVA. DOC gives an indication of the bulk organic content of a norm in a sample. UV254 measures the aromaticity of the norm. A sample with a high UV254 value indicates norm that has a high molecular weight, similar to what the HPSEC or molecular size distribution analysis would also tell us. And then we can also make use of SUVA, which is the specific ultraviolet absorbance. It's a calculation where we divide the UV254 by the DOC. A SUVA value between 1 and 5 is then usually obtained. A high SUVA value, in other words a 4 or a 5, will indicate that the norm is mostly humic and is more hydrophobic in character. And then the advanced technique, the MPRAM, will also give us similar information. It divides the norm into a hydrophobic, hydrophilic, or transphilic norm fraction. After knowing which norm fraction we need to target, we can focus on the appropriate treatment process or treatment technology. A previous WRC study compared different treatment technologies. They used the exact same treatment technology in lab on different source waters that they sampled throughout South Africa, and they found that not all treatment technologies perform the same. It greatly depends on your specific surface water. Why? Because the norm concentration and composition differs in various geographical areas, and norm character might also change seasonally. Take home message: norm is the main precursor to THM formation. Norm characterization techniques have been identified and is available. Before optimizing an existing water treatment process, it's vital to focus on the removal of specific or the problematic norm fraction in order to reduce THM formation. Not all organic compounds will react the same way with a disinfectant to form DBPs, since the character of norm differs. In other words, its molecular weight or hydrophobicity differs. And also the concentration of norm greatly affects the disinfection byproduct formed and also the amount of DBP formed. So it's very important that one investigate and determine the character of norm within the specific source water that you are treating. Thank you.
Alright, that is the end of the presentation by Dr. Sabiam Marais from Rainwater. I don't know if there are any questions. I saw that Jenny has already posted into it. One is a generic question or maybe just my own feedback on that. The programs have been prioritized in the National Water Transportation Master Plan. So the rollout of those programs again. That is all.
Dr. Ntantla, your voice is bad. We can't hear a thing.
Okay. change the animation a little bit. I'm not sure if you can hear me now. Can you hear me now?
No, we can't hear. It's just funny noise.
No, it's very bad, Nons. It's very bad. I think let's try and log on, and then maybe we can carry on with Mr. Klo with the presentation. Who the next presenter? Let me just check.
I just quickly check what good was in this.
Yeah. I think we can carry on with the program. Maybe Mr. Klo, you can go ahead with your presentation. While Notata is still trying to sort out the network issues.
Okay. Good morning, colleagues. My name is Dr. Chokwe from Capricorn District Municipality. I'll be sharing with you the lessons and experience in managing the microbial quality of drinking water. We use Capricorn as a case study. So in many countries around the globe, groundwater is essential in providing water supply to both rural and urban communities. And in the past, groundwater used to be associated with generally good quality, and it was less susceptible to contamination. However, recent studies have shown that the groundwater is susceptible to contamination. Capricorn District Municipality is a semi-arid region in the country where the provision of safe drinking water is inadequate. So the groundwater is the major source of drinking water in the district. Roughly about 80% of the population in the district receive drinking water using the groundwater source. Here, I'd just like to highlight that in the presentation, we did include the local municipality of Polokwane, as they get mainly, they got the bulk water from the Lepelle Northern Waters. The results here will be from Lepelle Nkumpi local municipality, Mole local municipality, as well as the blowback. So for the microbial quality of drinking water, normally total coliform and E. coli are used as indicators for pollution. These two microbes can be chemically deactivated using disinfection processes. Normally, the disinfection has already been alluded by the previous speakers, include the use of oxidant like chlorine, ozone, and ultraviolet, together with the chloroamines and chlorine dioxide, which is the most frequently used disinfectant. So for the study, chlorine was used as a disinfectant. Under the justification, so groundwater sources that are less vulnerable to fecal contamination still have a degree of vulnerability to be contaminated with the enteric viruses. So therefore, groundwater should be routinely monitored for fecal indicators such as E. coli and total coliform. The aim of the study was to assess the water quality, in this instance the borehole, in terms of microbial contamination as well as turbidity. We included turbidity because studies have shown that the turbidity have a direct relation with the disinfection processes. The higher the turbidity, the less efficient is the disinfection. So also we need to implement the disinfection processes during the water purification. In these instances, in our municipality, in some instances, we use the package plants where we use we have introduced reverse osmosis. We know reverse osmosis can take out the microbial during the purification. We also have chlorine at the reservoirs. We chlorinate at the reservoirs. In some instances, we chlorinate at the borehole. So on the methodology, we did a study. We took samples, historical data, we might put it that way, of 3 months from May to June. So we take 24 samples every month. So in total, we got 72 samples. and the samples were tested for E. coli, total coliform, and turbidity. We just need to mention that our laboratory is not yet SANAS accredited, but we do participate in proficiency testings for all these determinants with South African Bureau of Standard and NLA. Under the results from the study, we found that our E. coli as a municipality, we are sitting at 93% compliance, while the total coliform, we are sitting at 67% compliance, and the turbidity, we are sitting at 91% compliance. This is with the compliance with the blue drop system. So we are saying the mean results for the E. coli, even though they were less than 1, which meet the criteria, but the compliance it was still at 93. As I've already mentioned, then the results are not compliant towards the blue drop system, which got a target of 97. Also, the total coliform, it was not compliant. We are sitting at 67. The turbidity, we are the mean turbidity value was at 0.79, but the compliance was still at 91. We found in some instances, where we don't have where we are not disinfecting at the reservoir, we are disinfecting inland from the borehole. The turbidity is a bit higher, hence the compliance was low. Lesson from the study, we are saying the boreholes that are less vulnerable to fecal contamination, they still recorded a high microbial contamination. So in one of our local municipality, which is the Blueberg, it is on the far north. So there isn't much activities there. We don't even have a wastewater treatment plant at some of the sites, but still some of the samples there, they recorded high microbial contamination. And also the management of drinking water for microbial contamination, it will include the use of appropriate and effective disinfection. So in this instance, we are saying we must not have a one-fit-all system. We need to do individual assessment of our water supply to make sure we are using appropriate and effective disinfection. Also, we need to take care of our distribution system. In this instance, we need to implement a regular cleaning of reservoirs because the area is semi-arid, it's hot. The algae regrowth, because of the heat, it might be high. And also we need to have a qualified personnel for routine verification of water quality. As I've already mentioned during the WASH presentation, that in Africa we have a big challenge with capacity. Even at the municipal level, we are experiencing that challenge because we don't have enough people, trained people who can do who can look after our infrastructure and our systems. So in this instance, we need to measure residual chlorine frequently. And we did see that high turbidity values does interfere with the disinfection of the water supply. And then the intervention to manage the microbial contamination of the water, we are saying here we need to install some pre-filtration to remove some of the silt from the borehole before we implement the disinfection product to improve the microbial water quality. And also we need to do an operational monitoring of factors that will affect our disinfection process, such as temperature, turbidity, and pH. This need to be monitored regularly. And we also need to improve on our maintenance. We need to improve on the maintenance of the residual disinfectant in the distribution system to reduce the regrowth of the bacteria. And we also need to have a program that ensures that the responsible personnel are trained and certified. Because currently, in our process controllers, some of them, they are not certified with the Department of Water and Sanitation. And the training, I say, it can include in-house training and mentoring program, on-the-job experience, water association training courses, seminars and conferences, etc., etc. In conclusion, we are saying the CDM water quality was assessed in terms of the microbial and turbidity contaminants. The results show that all the determinants do not comply with the blue drop system. And we have also seen that the boreholes that are less susceptible to fecal contamination, they did record high microbial contamination. Microbial contamination, in some instances, they were reduced in areas where the cleaning of reservoir program were in place. And also we need to fill vacant positions with qualified personnel. I would just like to thank Capricorn District Municipality for providing the environment for the start. Thank you.
All right. Before Tobile comes in, I just want to check if I am audible enough.
Yes,
Much better. Much better.
Okay, all right, thank you. Apologies on my side for that break in transmission. I'm not sure really what went wrong, but I've tried to restart my computer and seemingly it worked. So before Dr. Chokwe did the presentation, I wanted to just also once more open the opportunity for anyone who has some specific questions. And I have been monitoring the Q&A, and I have seen Gary's question, which we are going to forward to Dr. Murray from Rainwater if that was not answered sufficiently in the presentation. But I mean, without taking away Dr. Chokwe's limelight, I would like to also thank him for the presentation and for sharing with us how they have managed to address some of the challenges with regards to disinfection, and also some of the recommendations that might really come in handy for other municipalities who might be struggling with maybe a similar problem. I see that there is a hand up from Mohau Ligupa. I just wanted to check if you have a question.
Yes, hi. I do have a question for
Please go ahead.
Dr. Chokwe. Yes, Dr. Chokwe, I would like to know that those boreholes that were susceptible to fecal contamination, as you found out in your presentation, is it because of sewage treatment plants, or is it because of I don't know, maybe industry around the boreholes? And then if so, the sewage treatment plants, do they return back the water back to drinking standards? Thank you.
Okay, thank you for the question. What we have found, there were some few boreholes, especially around the Mule area. One of them, I think it was along the river, and some of the contribution there might be the effluent from the hospital. But what we have done with that boreholes, we have implemented an inline disinfection where we disinfect right at the borehole. So in that borehole, we didn't have a package plant. So we disinfect before it goes to the reservoirs. So we did manage to lower the level of the microbial contaminants to meet the required standard. In others, especially in the blueback, where we did detect the microbial contamination, in most of them, we don't have a sewer treatment plant around. So we suspect this might be from cow grazing, and then during rain, they got permeated to the water table. Thank you. I don't know if I've answered all of your questions.
Yes, you have. Look, I just wanted to establish if there's any sewage treatment plants that are actually processing sewage waste back to sort of to reuse the water for drinking again, or all of it is maybe disposed to water system. You know, that's the main crux of my question.
Okay. Currently, in our municipality, we got oxidation ponds. So normally our sewer, they are not expected to be discharging to any streams because we don't have streams around. So in most instances, we might find there are overflows, especially during the rainy season. So that's where we tend to experience a high microbial contamination just from the overflow. But in other seasons like your summer, we don't have that much of a challenge. But as I've already mentioned, we might find some of this contamination, they might be coming from animal origin for the grazing and stuff like that.
Yes.
Thank you.
Thank you. Thank you.
All right, thank you very much, Mohau, for those questions, and also Dr. Chokwe for providing the responses. We really encourage such interactions, and also if there are any follow-up questions, please make use of the Q&A, because there you can interact even to a deeper detail. And also for the Water Research Commission, we are also listening in so that if there is anything really that needs to be addressed through research, then we can really maybe take over that part. All right, I see also there is a comment from Lien and Dr. Chokwe. Please look into that. All right, I would then once again would like to thank you, Dr. Chokwe, for sharing with us your experiences and some valuable lessons on how you manage or deal with some of the challenges within the Capricorn District Municipality. And once again, I would encourage that if any of the attendees would like to hear more, know more, please feel free to interact with Dr. Chokwe through the Q&A. And also, if you'd like to request Dr. Chokwe's email address, please do get in touch with us, or you can also request the contact details directly from him while he is here part of the event. All right, I would like to move on then to the next two presentations. I see from the program, they are both from Magalies. I can see Dr. Bahangwele Masindi here. So I just wanted to check if there is a different person doing the first presentation. Dr. Masindi? Unmute.
I think it should be the different person.
Okay. Then I would like to check if maybe Mr. Sandile Ngobo is a part of this webinar. Okay, I have not seen him, but then I think in the meantime, we're going to skip that presentation and then move on to the next one by Dr. Bahangwele Masindi from Magalies Water to talk about ensuring adequate drinking water disinfection. Over to you, Doctor.
Thank you very much. Can you hear me?
Yes, I can.
Okay. Like your chair has introduced, my name is Bahangwele Masindi from Magalies Water. Today, I'm going to give a talk on a topic entitled Ensuring Adequate Drinking Water Disinfection.
All right. Doctor, please put your presentation on slide mode.
Is it on slide mode?
Thank you. That is perfect.
Okay, no, thank you very much. Just to give a brief overview on disinfection. Disinfection is a widely used technology for water and wastewater treatment. It is mainly used for the attenuation of organic contaminants, inorganic contaminants, microbial contaminants. And within our water purification plants, we put disinfection in different treatment points or unit processes. We have pre-oxidations to remove some of the incoming contaminants that might affect the quality of our water. We also have intermediate chlorination, whereby we remove residuals from the pre-chlorination processes, and post-chlorination and booster stations to ensure that the water that we dispatch to different end-use points is free from different contaminants. So that's what we do. This is just pictures showing the type of raw water that we receive within Magalies Water, water purification entity or plants. So you could see we have the Velcadem with a very thick mat of hyacinth. And these plants, they promote anoxic conditions. And those anoxic conditions foster the presence of manganese and other ions, and also total organic carbon and microbial contaminants. And you could see these are the symptoms of upstream activities such as wastewater treatment processes, agricultural activities, urban runoffs, and other upstream catchment activities. And we as the downstream people, we suffer from the upstream consequences. And these are the symptoms. You could see the plants, and you could imagine the type of treatment that we need to put in place to ensure that the water that we dispatch to different end users comply with different specifications and regulatory requirements. And on the other one, the bottom left, you could see this is the Falkop Dam. And the top one feeds the Kalinin water treatment plant is the Velke Dam. The bottom one is Falkop Dam. You could see it's green in color. You could see algae floating in our dam. And you could anticipate the type of treatment that we need to put in place to ensure that this water complies to the drinking specifications. And this water in this dam is rich in algae, chlorophyll, total organic carbon, and microbial contaminants. And mainly because most of our wastewater treatment plants, when we did our catchment water quality monitoring, we realized that they are releasing water with high microbial load, and we as the downstream people suffer from that consequence. And on the other side, on my right, you could see the Rodiplat Dam Canal. This is the water that goes to our Klipdrift water treatment plant and also the Valmansdal water treatment plant. We also have a river, but it's just a tee-off that the water is split to the canal, the other one goes down with the river. You could see the algae floating in our water. The water is rich in algae, ammonia, manganese, iron, total organic carbon, and microbial contaminants. This is just a picture to show you that the treatability index of our raw water is quite high, and you need a lot of disinfectants to remove these contaminants, such as ammonia, being very problematic. We also tried the breakpoint chlorination, whereby you have to balance it at 8:1 ratio, meaning that the treatment cost that is required to try to bring water to the required standard is quite high. So we as downstream people, we suffer a lot. And these are some of the challenges that we experience within our water purification processes. We have the false chlorine demands. Mainly it's caused by unknown compounds. And this is the attention that I'm bringing to the Water Research Commission to say that, what if we need to detect these compounds and check whether this can be a potential research avenue? Because in certain instances, we had a situation whereby you put chlorine for pre-oxidation. When you monitor it, possibly after chemical dosing, you find that the chlorine is gone. There's no chlorine. When you go after the DEF unit, dissolved air flotation system, you realize that the chlorine is back into the system. So meaning that there's a compound that is consuming the available chlorine, then after a short time, it releases it back into the system. So these are some of the compounds that we need to check in our water purification system, because they give us false chlorine figures, and we at times end up overdosing or underdosing. So to regulate that, if we can know this kind of compounds, it might be quite important. Then emerging contaminants, I think, is one of the topical issue globally. Everyone is researching on emerging contaminants. They're trying to find solutions to remove emerging contaminants, their contribution to chlorine demand and all that, and evolving contaminants. Examples, we have the ARGs and all that. So those are the compounds that can contribute to false chlorine demands, and some of the challenges that we experience within Makali's water. And one of the topical challenges that we experience in South Africa, to be so general, you have the algal contamination. We have a lot of algae floating. You saw the Falkop Dam having high concentration. The water is green, essentially. So it makes it difficult downstream for us who do water purification, and also increase the treatability index of the water bodies and the metals, primarily manganese, because manganese can impart color. Manganese and iron can impart color into our water bodies, hence increasing the treatability index and also increasing the consumption rate of chlorine or our disinfectants. And high microbial load as well, the total plate counts, the coliforms, the E. coli, and all those sort of microbial contaminants and emerging contaminants. These are the topical or the burning contaminants that are really affecting our treatment efficacy within our water purification plants. So how do we do that within Makali's water? Which mitigation measures do we have in place to ensure that we get adequate disinfection? So we have ozones, not in all our plants, but some of our plants. I think 2 plants have ozone as a pre-treatment step. And we use chlorine dioxide for some of our plants as well, and liquid chlorine, whereby we don't have much of contaminants, maybe we only have TOC and all that. And also in plants which are heavily contaminated, we have intermediate chlorination, whereby we use HTH to ensure that our pre-oxidation is efficient enough. And when we do post-chlorination, we don't experience much of the challenges within the distribution systems. And the benefit of having strong oxidants on pre-oxidation is that you eliminate distribution challenges. You're not going to have a lot of microbial failures and also color within your distribution system. Hence, we opted to use strong oxidants such as chlorine dioxide and ozone. We reduce the chlorine demand at the dispatch point or the distribution points, and also reduce microbial regrowth. Because if you could remove all the compounds or all the contaminants that consumes a lot of chlorine upstream, when you go to the downstream of the process where you dispatch the water, you don't have much of the demand within your raw water resources that you are distributing to different end users. So these are some of the pre-oxidation initiatives that we put in place to ensure that we have adequate disinfection within Makali's water. Then also other initiatives that we put in place to ensure that there's adequate disinfection within our post-chlorination system or our dispatching points. We are planning on installing boosters, because in one of our plants that is vastly dispersed, it is a distribution system that goes up to 100 kilometers. And you could expect that chlorine will dissipate along the way. You have different chlorine consumers within your distribution network. So if we could install chlorine booster, but this will be informed by the chlorine decay and demand studies. You need to understand at which point within your distribution system you're gonna have chlorine dissipating or being consumed completely in a way that you're gonna have microbial regrowth. So if you can do that study, it's much more easier for you to install chlorine boosters, and also trying different algorithms, the combinations. For example, in one of our plants, we are using chlorine dioxide as a pre-oxidant and liquid chlorine as a post-oxidant. But now we also try to, we want to try a vice versa. We want to put liquid chlorine as a pre-oxidant and try chlorine dioxide as a post-oxidant and see the efficacy and all that, and check if whether we're going to comply with the SANS 241 specifications, and also to determine the forced chlorine demands and also modeling the demands. There's something that we are doing as research. Actually, we are doing with the Council for Scientific and Industrial Research, whereby we are trying the hydraulic dynamic model. This model it gives you real-time data, whereby if the chlorine is dissipating in a certain point, it will inform you that you need to increase the chlorine dosages. And we also installed different meters, the chlorine residual meters, the pH meters, the turbidity meters. So they are shown in our SCADA. We could see at what point within our distribution system, a certain compound or a certain water quality determinant is going beyond the required limit. Then we act quickly. So this is some of the interventions that we have put in place to ensure that our distribution system complies with the required specifications. And also trying the chlorine dioxide, I've mentioned that one. And lastly, checking the catchment to identify the culprits within the catchment and the type of contaminants that you should expect downstream when you do your water purification. If you have an effective catchment monitoring strategy, it will really help you a lot in ensuring that you put the right chemicals in place and to ensure that you don't have water purification challenges as you purify the water and as you distribute the water to different end users. Then what we have as Makali's water, the approach that we have put in place to ensure that we always provide water that complies with SANS 241 specifications as mandated. We have chlorine dioxide as our pre-oxidant and liquid chlorine as our post-oxidant. We, in some plants like Falcop and Clipdrift, we have ozone and also liquid chlorine for post-chlorination. We have liquid chlorine and intermediate chlorine. When the demand is quite high, we also add HTH in the intermediate to ensure that the disinfection is efficient. We remove all the contaminants that are coming into our water purification plants. And for post-chlorination, we use liquid chlorine. And liquid chlorine versus liquid chlorine, we usually do that in some of the plants. We have one in Cullinan This is the smallest water purification plant we have within Makalis Water. We use for pre-oxidation, we use liquid chlorine, and for post-chlorination, we use liquid chlorine as well. But because we have seasonal challenges such as high level of manganese that comes on seasonal basis, mainly during summer, you have high manganese concentration. So we always switch on to chlorine dioxide, and we do post-chlorination with liquid chlorine. So this dynamic hydraulic model, we have installed it to ensure that we always supply water that complies with different SANS 241 specifications and also the World Health Organization standards. So we do that to be very proactive and to be very responsive in some of the challenges within our distribution networks. So we also regulate our storage time, because this model can tell you that now the demand has increased, then the pumping rate will increase from the plant or from the reservoir and all that. And we get the real-time results all the time in terms of residual chlorine and all the other water quality determinants. We have meters installed in some of our reservoirs, some of our dispatching points, and also the point of sale. And so far, this combination has given us the desired results in terms of adequate disinfection. We don't have much of the challenges in terms of disinfection within our distribution networks. And for us, mainly to achieve that, we have a pilot plan that we subject those chemicals and those combinations before we could really take them to a larger scale. It's more of a risk control strategy, whereby we do most of our basic research and piloting studies before we could deploy any technology into a live system, and to minimize any risk, because it's quite a sensitive resource and there's people's health at stake. So we need to regulate that. So we subject most of our technologies, different chlorine combination within this pilot plant, and check the potential end product. And with that being said, I should thank you very much for your attention.
All right, thank you very much, Doctor, for that wealth of information that you have just shared with us. And from the Water Research Commission point of view, we are more than happy to engage further on any potential research questions that we might need to look into for our next call for proposals. But maybe before we do that, some of the aspects that you spoke about, there are other experts in this webinar. If there are other additional inputs, we can take those inputs. And also, if there are people who are also interested in the work that you are doing in terms of maybe partnering with Makalis Water, or maybe just having some sort of an engagement or exchange on how each one addresses some of the problems, please feel free to engage with Dr. Masindi through the chat function, or if it's a specific question, you can also type out that question through the Q&A box. But thank you very much for that very insightful presentation, Doctor. I see that there is a note from Mulalo who says, can you please share the notes? I am assuming that this is the presentations. So Tobile will share all the presentations from today once we have received consent from today's speakers. So I hope that addresses your question, Mulalo Mhlanga. All right, we are going to move on since I do not think that there is a second presentation from Makalis Water today. If I understand it very well, it was supposed to be done by Mr. Sandile Ngobo, but I do not see him in this event today. So we are going to move right ahead and open the platform further for any other discussion, questions, and last comments before we proceed towards the end of our webinar today. So I would like to just go a little back, and I have noted some questions from Lian. I assume that is a question that was directed to Dr. Chokwe. And I also saw a question from Gary, which was also addressed to Dr. Chokwe, but that is just a request for contact details. Yeah. All right, Dr. Chokwe, there is a question. Have you checked for crypto and Yardia analysis, and how deep are the boreholes? I don't know if Leanne, you would want to maybe elaborate further on your question before Dr. Chokwe answers.
Thanks, Nhlanhla. Yeah, I was just thinking that if the boreholes are fairly shallow and they are contaminated by cows, then that is a risk factor for me for crypto and Giardia analysis. So that's why I was asking that question.
Okay, thank you, Leanne, for the question. Currently, we are not testing for crypto and Giardia because of capacity. We don't have enough personnel in the lab and the equipment as well. And then in terms of the borehole depth, currently our borehole range from 56 to about 130 meters. Thank you. So I couldn't answer it on the chat. It seems like I can't post anything on the chat. So, but that question I've answered it under the Q&A.
Thank you, Dr. Chokwe. I think, yeah, crypto and Giardia are quite difficult to analyze. I wouldn't suggest that that kind of analysis is done at your lab. I think that's better to send that out to a lab that's already got accreditation for it. The boreholes are quite deep. Have you done any geohydrological analysis on them in terms of where the water is coming from the aquifer?
No, we haven't done that. You know, the system here at the municipality, sometimes it works differently in the sense that, you know, when there is a need, you know, we are 4 departments within the infrastructure, and I'm in the water quality scientific service. We've got the planning, the implementation, and the O&M. So most of the time, the drilling of the borehole, they'll be from O&M and implementation. We'll only come in as water quality to check, you know, if we need to install a package plant, it mainly just to check the quality of the water. And then on your question on the crypto, yes, every year we have a program here where we outsource the analysis of all our science determinant on to the accredited lab. And then for the past 3 years, we have been picking up the crypto and the Giardia. But as a monitoring tool, we don't have that capacity to do that. Thank you.
Thank you very much.
All right, thanks colleagues for those exchanges. I have been checking the chat box for further questions, but I see none. And also seemingly all the questions from the chat and have also been attended to. And with that, that brings us to the end of our technical session. And at this point, I want to sincerely thank our speakers for today, starting from Leanne on the insights on what the new standard, drinking water standard, SANS 241, will be bringing in. And just to reiterate, this is a sector document, so it will be distributed to the sector for comments and also to give you also time to also prepare for the new standard. And then also I would like to thank our international partner, Mr. Samuel Diarra from World Vision for those insights that he shared on the management of lead in rural water supply systems. And once again, if you are struggling with a similar problem, please feel free to reach out to us and then we can put you into contact with Mr. Diarra. And then also Prasantha from Umgeni Water, who was leading a WRC project. And I saw a question earlier on whether the report is available or not. So the report is already available on the WRC website under the Knowledge Hub function. So please feel free to access our website and type out some keywords and you should get that report. And if you are experiencing any problems, please also contact us and then I can send that report to you. And then also we had the presentation from Dr. Safia Marais from Rainwater on formation of disinfection byproducts. And once again, if you have any more specific questions, please also let us know, then we can put you into contact with any of the speakers. And then I would like to then further to thank our municipal partners for presenting some practical solutions on how to ensure adequate disinfection within their various systems. And also from these two presentations, we've learned quite a lot, and also we've taken note on some of those outstanding issues that might really require some further engagement, either be amongst ourselves for those that really had similar problems in the past, but have managed to address them. So if we can maybe continue sharing that information, that would certainly be helpful rather than to immediately go for a research project. So I would also like to reiterate that the municipal roadshows, these are regular WRC webinars that will feature quite strongly in the future going forward. So we would like also to hear from you what other topics that you would like this platform to address, other than us really picking out a topic that really we might not even know whether it will be helpful or not. So please do send us some your ideas. You can send it to Tobile, or you can send them through to me, and then we'll be able then to co-convene or co-conceptualize our next roadshow. And then just before then we close, I do not see Salga, Mr. William Moraka here. I would just like to do a quick check on our chat function and Q&A, just to make sure that there aren't any questions that really we are skipping. So I see there is a question from Mohau. What is the cost of disinfection per liter with chlorine and various other methods as compared to the rest of the world? And then Mulalo is asking, how often do we do such webinars? And then I've also taken note of Gary's comment there. We will definitely provide a response to your question. I'm taking it that it was that time where there was a break in transmission, but my answer to the Blue Drop program was that it has been reprioritized under the National Water Sanitation Master Plan, which really is undergoing implementation. So the exact date as to when the program is going to resume, I would not have that specific answer, but just for today, rest assured that it has been reprioritized, and in the near future, we might see or get a communication in this regard. And then the other was on the request for Dr. Chokwe's email address. So we are going to leave that to Dr. Chokwe, and he can distribute the contact details in the chat function. All right. To Mohau's question, so if either Dr. Chokwe, Prasantha, and Dr. Masindi, I would really encourage that maybe Mohau, you engage further, because I mean, there wouldn't be one answer to your question. So you can engage with these colleagues from water boards and municipalities, and then you can get even a more specific answer, because it will vary from one municipality to the next. All right, on the question on how often, the idea was to have this quarterly. So like I've already said that for our next one, for the next quarter, which is January to March next year, we will be looking forward to your ideas on which thematic area or topic you would like the Water Research Commission to address in our next roadshow. All right, colleagues, I don't see any other questions. So like I started off by saying, I would like to sincerely thank our speakers and mention that you will be receiving an email, a request from us, so that we can share your presentations if that is okay with you. And then once we have received your consent, and then there will be an email from Tobile distributing the presentations and the recording for today's meeting to everyone who registered today. And then with that, I would like to thank even our participants for being interactive, and also just to say once again that we really encourage such interactions, because this is a platform where we can share some experiences, some lessons, and then also help another person in another municipality solve a problem that you would have already maybe overcome. So thank you very much for that, and we encourage that you continue. If there is someone's email address that you would like to request, you can do so, make that request, and then we are going to forward that request to that relevant person. And then through that, then you can then continue interacting. So from me and the Water Research Commission, and also Tobile and Zama, who also helped get this event together, as well as Slengiwe, I would like to thank everyone and wish everyone the very best for the rest of the afternoon. Thank you and bye.
Thank you, Chair.
Thank you.
Bye-bye.
Thank you.
Thank you. Bye.
Thank you. Bye.